we, by the grace of God, will be completing the SPSS class today, and then by Tuesday we'll start the Stata class, although that will be facilitated by one of us. And I want to think that this SPSS class will be able to grab one or two things. So, but before we call it a wrap, we are going to cover the last part of the inferential statistics, which is the usually the most important part when you are interested in doing what we call modeling, in fitting statistical models. So this is very needed. It's a very important part of inferential statistics. So these are the hypotheses that we've been able to test so far in this class. See them highlighted in yellow. So, and the one left is this hypothesis number 4, saying there is no relationship between BMI and age. So, I think we even did this last class. We were able to do a correlation, a Pearson and the Spearman rank test. So, but the other one, which is talking about, sorry, let me go to the previous slide. Yeah. So the other one, which is talking about simple and multiple linear regression. So I think I remember saying this during the last class, that correlation test can only tell you whether there is a relationship. It will not tell you if it will not quantify the relationship. So that's the that's why we'll be needing simple or multiple linear regression test. So excuse me, please. This one's a break up. Okay, so let me move on to this table. I shared a document with us on the group. I think interacting with that document will help us to understand some statistical tests. There are a lot. I can't share all of them. So it depends on what you are doing. And like I said during one of the classes, that if you, in the course of your job, you encounter a need for a test or any statistical tool that you need to use, or techniques, and you are not getting it, you can reach out to us to provide support. So for simple or linear regression, look at it. This one is to test linear relationship. So when we are talking about linear regression, it's testing linear relationship. I'm sure we all had this even during primary school. I think they're now doing linear equation, where they will tell us y is equals to 2x, find x or find y. I'm sure most of us did that. So that's an example of a linear equation, a linear regression, so which is measuring linear relationship. So that's what we the first one we're going to consider in this this evening. So number one thing, for you to run a linear regression, you should be talking about two quantitative variables. So for instance, now let's go back to correlation test, the hypothesis for correlation test that we did. So we have BMI and we have age here. So both of them, they are quantitative data set, variables rather. So that's why we're able to run a correlation test. But the weakness of correlation test is that it will only tell us there is a relationship. It will not tell us the direction or the quantity of the relationship. So that's why we need linear regression to measure that. So for us to conduct a linear regression, what do we do? Let me go to the SPSS environment now so that we can try that out. So our interest is to want to first do what we call simple linear regression. It is simple when you are dealing with just two variables. You are dealing with just two variables. It is simple. So want to copy this and okay. So okay, so if you are interested in just BMI and age, and we are interested in knowing the direction of relationship. So it will no longer be, so the null hypothesis will no longer be just there is no. We may be interested in saying there is no negative relationship between, or we'll say, we can even say BMI, body mass index, does not increase as the age increases. So that's the interest. We are interested in establishing this, or simply put, you can say BMI does not increase with age. So age, yes, that's what makes it. That's what makes it a. That's what makes it a quantitative. So look at now. We have BMI quantitative. We have age in years quantitative. They are just two. And our interest is not just to establish relationship. We want to know what is happening. Is it that when the age increases, the BMI increases too? So you want to try out a simple linear regression. Simple linear regression. Okay. Yeah, so that's for simple linear regression. So let us go ahead now and do some statistical tests. Okay, so for us to conduct a simple linear regression, again, you come to analyze. So then on this tab, you try to locate regression. So look at it here, and there's another box here. You scroll down to linear. So this is what we want to do, linear. So you click on linear. Now, the question is, which one is a dependence variable? Which one is the independence variable? I'd like us to unmute. We've been interacting on how to identify which one is dependent and which one is the independent variable. So I'd like us to demonstrate that here now. So our interest is to do BMI and age. And remember, look at it. So we are running simple linear regression for BMI and age in years. So which one is the dependent variable? So I'm waiting. So I'm waiting, please.
Sir, you mean which one is?
So
Hello,
of BMI and age. Yes, I can hear you.
Yeah, we actually say BMI is independent. Oh, is dependent. Why age is independent? BMI. Yes, because the age will determine the BMI.
Correct.
So the lower the age.
Thanks. That shows you are flowing with. So the dependence variable is just from the word depends. Which one depends on each other? Of course, BMI is from weight and height. So your weight depends on your age. Your age cannot depend on your age increases is whether you like it or not. As day is running by, your age will increase. But it doesn't mean as day is going by, it doesn't mean that your weight or your height has to change. It doesn't mean it's not changing for everybody. There are some that are stunted. So since BMI is derived from weight and height, so we now ask that, okay, if your age is increasing, what happens to BMI? So it means BMI is the dependent. BMI is depending on age. So that is it. So then let us now go to the first box here to see the statistics we would like to report. So yeah, for me, I'm interested in the coefficient, the estimate. And I may also be interested in the confidence interval. This is also good to report it. So I think that's fine for now. Yeah, I think that's fine. So I'll click continue. So if I'm interested in plotting the graph, I could also do that too. But I'm not, that's not the interest. But if you like, you can do normality curve, you can do, and also to say, please, simple linear regression also assume some assumptions. So simple linear regression is also following a normal distribution. So you should also establish your normality, and then before you go ahead with the test. We've done all of that. So I want to click OK. So for this selection variable, case label, weight, that's for if you are for instance selection variable, you are interested in running the model, doing a kind of stratification based on the variable you want to use as selection variable. So then the label for case. Then if you are doing weighting, you can also select the variable here to weight. So, but here we are just running a simple linear regression. So I hit OK, and let's have the results. It's the regression is running now. Remember this data set is a large one. So let's allow it to complete the model fitting. Okay, please, what's going on here? Okay, great. So we now have our results. So again, remember I said SPSS, that's one thing about SPSS. SPSS is going to give you a lot of results. So it is you that will now identify the one that answers your objective or your hypothesis and then report it. So look at it now. We have a table showing the variable removed. No variable was removed. Of course, this is a simple linear regression. So then we have the ones showing the model summary. So this part is very important if you are fitting a model. This is telling us the information about our model. So it's giving the R square, it's giving the R value, and then also the standard error. So this like evaluating the performance of that model we are fitting. So the R square is really low. That's not the concentration now. ANOVA also is reported. So this is where we are coming. This is a model. You can see it, model. So this is what we have just done. And when you are running a simple linear regression, your interest, let me show the, so when you are running, so this is a model. So this is how the equation looks like. So when you are running a simple linear regression, you have the y, you have the b, which b naught, which is the intercept. And then here we have the coefficient, the b1, the coefficient, then x is that our independent variable. And then the error term here, it's is a random deviation. So that is, so in interpreting this, of course, we understand y, we understand x. So what is b, what's the b naught? And then what's the b1? So the b1 is the one telling us the amount of change for each unit of x. So please, I want us to understand this. This tells us, this shows us how to interpret the results we get from the analysis. Is the y, I mean, B1 is the amount of change in y for each 1 unit change in x. So in this analysis now, our B1 is actually the amount of change in BMI for each 1 unit change in h. Are you getting it? So let's go back to that result. So again, yeah, so this is our B here. This is a B1, the coefficient. So it's 18 point, sorry, it's 18.433. So let's say we report 18.43. And then you come here, you look at the significant, the p-value. So the p-value, this is telling us whether this model, this variable h, is telling us whether it's significant or not. So, but see, so b is a constant. So if you come to, yeah, if we come to here now, our model, if we are going to write out the model now, so our model becomes, so excuse me, please. Yeah. So our model becomes y, which is BMI. I need you to see what I'm doing. Yeah, great. So our model become BMI is equals to 18.43, which is the coefficient, our beta naught. So then plus 0.15, 0.15 in bracket h. So that is it. That is it. So please, sorry, I'm so sorry, that was an error. What we interpreted here as 18 points as the beta the other time is the constant, not the. So we're saying that as age increases by 1, BMI increases by 0.148, or approximately let's say 0.15. And this is now making sense. And one thing we do in medical, when you analyze medical data, we don't only work with statistical significance. We also talk about the clinical plausibility. Is this plausible clinically? So we don't often report medical data in isolation of what clinical practice is saying. So the question now is, we have just done a simple linear regression. What is multiple linear regression? So here, we want to talk about multiple. So it's multiple when you have more than one independent variable. So let's say we have age here, and then we also want to check which other, let's check the data, which other quantitative data do we have that we can regress. So weight was derived, BMI was derived from weight, you cannot use it. Age. So unfortunately, we don't have any other, and I should have just, so, but anyways, let me just, let me assume birth month here. Let me just assume it's also quantitative data. Please don't, okay, let me use that, let me use this. So don't misinterpret the birth month is not quantitative. When you are running simple linear regression, remember you also need your variables to both of them to be quantitative. So let me say I want to do, remember age and birth month. Okay, I think it's even wrong to use that. So I'm going to use, because age was derived from birth month and birth year. So we also cannot use that. That's a result in collinearity. So let me, yes, good. I want to use, okay, so let me use this relate, although I don't know what it's all about. Respondent, okay, respondent relationship. So please, I'm just assuming this relate here is a quantitative data. So now I want to do a simple, a multiple linear regression. So I'm adding variable relate to this. So so let's put it like this. And now, okay, we go to analyze again. For us to do multiple linear regression, you still come to regression. It's the same process. Then you click linear. So let me reset it so that I'll pick it again. Remember, our dependent variable is the BMI, and now we have independent variable H, and we want to use where is that variable? Yeah, this one. We want to use it as we am assuming that this is a quantitative data. So I want to use it in addition to H so that my model will now become multiple. So like I said, it is multiple when your independent variable is more than. You can have, depends on the model you are fitting, you can have up to 10, 15, 20 independent variables rather. So, but the moment your independent variable is more than one, the model you are fitting is no longer a simple linear regression. It becomes multiple linear regression. So I'm going to put this and then come to statistics again. I'm interested in the confidence interval as well. So I click OK. Continue, then I click OK. So let's wait for the result and say, okay, so the result is here. Look at it. So our new result is showing the information, the result for both age and the respondent relationship to household head. Now, for regression, for linear regression, it's possible that you have positive coefficient, and it's also possible that you have a negative coefficient. They both have implications. So here now that our results returns 0.148 for H, you can see that it has adjusted a bit compared to when we did only, no, there is no difference. It's still the same thing. That shows there is no confounding variables. So now, this is now telling us that our first variable 0.14 and then respondent relationship to household head is minus 0.00. So this is telling us that as the household head is is decreasing, that's when BMI, as a number of household head increases, then our BMI decreases by 0.002. That's why it is negative. So when it's negative, it means decrease. It means it's going down. But when it's positive, it means the BMI is increasing by. So if we want to write the equation for that too, we want to say BMI is equals to the coefficient again 18.44 plus. So now we have more than 18.44 plus 0.1. Let me say approximately 15 age, and plus minus. Okay, so this is now minus 0.002 household head. Let me just call that one RHH. That's what it is. So if you are to get the BMI, you have to get the BMI value. I'm not trying to go into mathematics class. So if you have to get the BMI value, what the BMI be when age, let's say age is now 10. So when age is 10, what's the BMI? It's to just lot uh, for this the multiple linear regression. You slot, let's say the age is 10, equals to 10. Let's say relationship to household head. Let's say it's 3. So you just slot 3 here, you slot 10 here, then you get the BMI. But that's not our interest. For our statistical interpretation here is to let us know what direction. When age increase, is BMI increasing or going down? So say you now have up to 10 independent variables. You can put them there. You can put them there to also see the performance to see. So usually our interest is to know what is causing what. Although you cannot use this type of data that we are using because it's a cross-sectional data. You cannot use it to make a causal inference. But you want to say what is determining what is influencing what is affecting what. Is it that let me try to leave medical data a little bit. Is it that when the amount you spend on advertisements, when it goes up, your sales goes up or comes down? So that's what linear regression will help you to answer. That's the kind of question it will help you to answer. So that's that. So we also want to okay, let me ask, does anyone have question on this before we move on to logistic regression, which is the last model will be fitting this class. Is if you have any question, you need further clarification, kindly unmute and then ask now. Thank you.
Thank you very much, sir. This respondent relationship to household head, I'm not that clear about that one. What does it actually stands for? And what does it do?
Okay, thank you. Please, that's why I said the reason I used it was I just needed to demonstrate multiple linear regression. But unfortunately, in this data set, I don't have other quantitative data. So if I'm fitting a model, normally I'm not going to use that to fit my model. Do you get it? But to answer your question, what is it? That's why in every data set, you understand the label. So this one is saying respondent's relationship to household head. So normally in the data, one is telling us that the person that is answering this question, this survey, that is answering the interviewer is the head. Are you getting it? Is the head of the family. So they're asking what's your relationship with the head of this household? I'm the head. But for those that had them two entered for them, when they ask them what's your relationship with the head of this household, say, oh, I'm the wife, I'm the daughter, I'm the son. That's what those values mean. So normally I'm not going to use this variable to fit a model because I may not be interested in seeing how household head. Because that's why we said clinical plausibility is also important. How will your relationship to the household affect your body mass index? And well, if you think very well, it may. For instance, in an household where it's expected that those who are sorry, please. In an household that it is expected that those who are close to the household that they enjoy more than those who are not directly, maybe like maid or the likes. Well, you may say maybe they are not well fed, they are malnourished, kind of, and then it will affect BMI. What's BMI basically? Assess is the malnutrition. That's the variable used to measure malnutrition among adults. So it's Of course, it's may. So that's what the variable means. But because we are fitting linear regression here, I will not say this is what I want to use. I want to go strictly with quantitative data set. Yeah, I don't know if I've answered your question.
Sure, the illustration was clear and simple, sir.
Thank you. Any other question, please? Okay, so if we don't have any other question, let's move on to the logistic regression. So logistic regression is very common. In fact, I would say it's the most common statistical model used in medical data. And the reason is that logistic basically is used for binary outcomes. Okay, no, not binary outcome, for categorical outcome. So when I say outcome here, I mean the dependence variable. Let me open brackets, dependence variable. So yeah. So, but there is a very common one, which is known as binary logistic regression. It's the most common one, sorry, it's the most common model in using medical data. And the reason is because it has binary outcome, 1 or 0. 1 or 0. Yes or no? Yes or no? Dead or alive? And you know, those are the common outcome you see in medical data. Dead or alive, well or unwell. So things like that. So each time the outcome variable, the dependent variable has just 2 categories. When it has just 2 categories, then and you are interested in fitting a model, you want to look at what is the relationship, what is the association, what is the predictors of, what is predicting what. We use this a lot. I would even say it's been overused. So the simple, okay, I'm going to use I think the only binary outcome variable that we have here is the pregnancy, yes or no? Yeah, that's the only way. Let's run a quick check to see if it has just 2. It has just, okay, this is it. Let's check if it has just 2 groups. And here, of course, it has just 2 groups, yes or no? Remember, I said you only fit binary logistic regression when you have 2 groups. So, okay, that's good. So what if you now have variable that has more than 2 groups as your outcome? So we also have the one we call multinomial logistic regression. And then we have the one we call ordinal logistic regression. So yeah, so multinomial is when you have more than your outcome variable is more than 2 groups, but the order does not matter. The order of those categories does not matter. That's where you use is if your outcome variable has a category like let me see from, okay, that's a grouped BMI. I have it here. Oh, okay, I don't have it here. That BMI that we categorized, I don't have it here. Okay, let me say, for instance, it doesn't make any sense to say you want to use age as a dependent variable. It's usually independent. It's only God that determines your age, the time you were born. And then, so no variable will determine your age. Okay, so which variable can I then use? Or can we use, let's use religion. Yes, thank you. Let's use religion. Let's use religion. Religion. Great. So I want to see. Okay, so religion has many groups. I thought we have a regrouped religion variable. Okay, we don't have it. Okay, great. So let's use religion. So for instance, now if religion is our outcome variable, and let's say religion, outcome variable, outcome, outcome variable is religion, and it has categories we have in it is we have Christian, Muslim, we have Christian, we have Muslim, we have, let's say we have others. Okay, traditional, and we have others, right? So this is more than two groups. These are the traditional. So these are the categories in that variable religion. It's more that there are those categories. There are more than two groups. 1, 2, 3, 4. So you cannot use binary again. Then you can use multinomial because the order does not matter. Of course, you cannot say Christian has a higher rank than Muslim. So you can't say traditional has a higher rank. Unlike if you want to use a level of education, you and I know that. Okay, let's use that as, let's say our variable here, outcome variable here is variable is level of education. So let me we can see very well. Level of education, group that's none, primary, secondary, tertiary. Now, tertiary. Now, we all know that someone who has no education, you cannot say is at the same category with someone who has primary education. No. So there is an order here, and the order is important. That's why we have to use ordinal logistic regression for this kind. So, but in situation where there is no order, the order does not matter. Each can come. So at any of the, it could be the first group, it could be the second, either ways. So in such case, you use multinomial logistic regression. So let's use religion. Let's try it out now. And just like we demonstrated simple and multiple linear regression, it becomes multiple regression. It becomes multiple logistic regression too by the time you put in more than one independent variable. So we go back to Stata. We want to demonstrate binary logistic regression now. So I want to use the variable pregnant. Yeah. Wait, let me double check again. Uh, okay, yeah, look at it. Okay, so we didn't put, so let me just use pregnant, yes, no. That's the variable we have in the data set. And so now we are going to demonstrate that now. And okay, so which independent variable are we using? We are going to use age group. We are going to use age group. Can also use religion. But first of all, we'll demonstrate the simple binary logistic regression. So there we go. Now, again, you come to analyze. then we come straight to regression. So, you know, the first one we used for linear regression was linear. Now we are interested in binary logistics. So look at it, just like I mentioned, then there is binary, there is multinomial logistics, there is ordinal logistics, there is probit, but I'm not taking us to that for now. So binary, which variable am I using? So let me up this. So this is it as a dependent. I want to put it here. Now, covariate is the same thing as independent. So anywhere you see when you say covariate, it's the same thing as independent variable. So because I'm interested in fitting just simple binary logistic regression. I'm just going to put H, only one. I get it. I'll put only one. Now, I have categorical variable. Here, let me remove it. You can see that before putting it here, it's not even popping up. So I want to come here to specify the grouping. So I'm going to put this, I'll put it here. So, and then this is just for me to say which one I want to use as my reference category. So, okay, maybe let me just go back a little bit. Let's go to that so that we can be on the same page. Okay, great. So these are the categories in that new variable, that H variable. So I have the category 15 to 19. So, and each time you are reporting logistic regression, you will be using a group as a reference because you are saying this is this compared to this group. So what we want to do here in this categorical is to tell which one are we using for reference group. So I will just come to the covariate box here, and I'll come and put it in categorical. So here, the default is last. That is going to use the last group as a reference group. But me, I want to change it. It depends on your interest and how you want your results to look like. For me, I want to change it to first. And then I'm just going to click OK. So once I click change, you can see it has changed to first here. Now I'll click continue. Then I'll click OK. I don't need selection variable. And then here, it's if you are running multiple logistic regression and you want each of the variables imputed, maybe you want a forward imputation, you want a backward, you want conditional. So this way, but here we are not indicating any. We just want to do the common logistic regression. So yeah, we have the results now. Look at it. So again, SPSS will give you more than enough results. So you also need to understand which one do you need to answer your question. So this is just describing what you just do. It's a case processing summary. It's telling us the total number of data. Use the case selected here. There are 15,768. You know, it's a large data set. So how many is missing? None. You can see none is missing. And then look at it. The code used for no that those who are not pregnant or unsure is 0, and those who are pregnant is 1 in the so this also describes each of the groups of the categories. Now, the the important result here is this one. This variable in equation. This is actually our result for a simple logistic regression. So when we are conducting logistic regression, we are not interested in reporting beta. We're always interested in reporting exponential beta, which is referred to as odds ratio. We call it odds ratio. So for me, if I'm reporting these results now, I'll just pick the odds ratio and I'll pick the p-value, which is even significant. Are you getting it? So I'll pick the p value. Okay. Now, 1 hour gone. We still have some more time, so we'll soon finish. So yeah, this is now the main result where you get to interpret each of the age group. Like I said, you remember we used first group as what? As a reference category. So this is another problem with SPSS, which I feel by the time you start using Stata, you see Stata will put them out clear. So here is the first age group. Here is the second age group. Instead of SPSS reporting the categories, it's just telling us 1, 2, 3. You get so this is the first, this is the second, this is the third, this is the fourth. So based on what we have in this categorical variable, so meaning the first group is 15 to 19, second one is 20 to 24. So by the time we want to, let's report, I want to report the second one here, comparing it with the first group. Second one is 20 to 24 years. And then now the result, which is the odds ratio for that, is saying that those who are between the age of 24 to 20 to 24 years old. Look at it, those who are between this age group, they are more likely to be pregnant because the outcome variable here is 1. They are more likely to be pregnant compared to those who are between the age of 15 to 19. That's what the result is saying. And I think that makes sense. So the same thing, you can see that it's increasing. By the time it gets to the next age group, it has increased. Of course, as women grow older, their chances of getting pregnant also decreases. Look at it, you can see that it's coming down. You can see that the odds ratio is coming down. The chances that they will get pregnant has reduced here. And look at, by the time you get to age group 5, what's in age group 5? Age group 5, 40 to 44. That's very correct. By the time they get to 40 to 44, you see that they are, so anytime you are reporting logistic regression and your odds ratio is less than 1, we report it as less than, we don't say they are more likely. You know, this one is saying they are more likely. This one is saying they are less likely compared to the reference age group. Those who are between 20 to 24, they are 2.7 times more likely to be pregnant compared to those who are between the age of 15 to 19. And if you come to the last one here, those who are between the age group of 40 to 49, is saying that they are they are less likely, 0.1 times less likely to be pregnant compared to those who are between the age of 15 to 19. So that's what the result is telling us. Again, if your interest is to run a multiple binary logistic regression, it's simply that you want to add more independent variable. And it's as simple as, so let's just add another independent variable. We want to add religion to this. So religion, we have to also go and put the category. And if you do not put it, SPSS will use last as the, which is the default. It's going to use the last age group. But me, I'm going to use first category here. So I'll select here, select first. Here, I want to change it. I'm changing it to first. It has changed to first. And I'll click OK. Then I mean continue. Then I'll click OK here. Again, we have all our results. So our interest here is the model. And the one that shows everything here, see, is the last table here, variables in the equation. Just look at, so these are the results for the age group, and these are the results for religion. When you are doing logistic regression, please, I beg you, don't go and make mistake and present results for in the coefficient. This is just by default, SPSS will give you, but you don't need it. You need to come to the exponential data. And it's also mathematical. If you carry your calculator, if you press exponential 1.017, it will give you this value. I get it. So it's just to exponentiate your beta. That's how the logistic regression concept. So we report odds ratio for logistic regression. So that is that. Again, if your interest is now to do, they all have the same concept. If your interest is now to do a multinomial logistic regression, here we want to, meaning that we have an outcome variable that has more than two groups. So let's say someone approach you now and he has a data he wants to say, okay, I want to look at predictors of religion in maybe one part of the country. Are you getting it? And he's interested in Christian, Muslim, traditional, for instance. That's already more than two groups. So you cannot go and be telling the person to do a binary logistic regression. That would be wrong. And you cannot tell the person to do ordinary logistic regression. That would be wrong too. So the appropriate regression to report, to conduct here, is to what? Is to do a multinomial regression. It's simple as well. Just come to analyze, come to regression. So that's a good thing about SPSS. You don't need code, you don't need, you can even complete your analysis without writing single code. So again, you come to multinomial here. Got it? Multinomial. So we want to use religion as our dependent. Then click on it, put it here. And then we want to use age group. We want to use age group as our covariate. We also want to use, let's say we want to use ethnicity. Yes. Let's say that's, I'm already doing multiple multinomial logistic regression. So I can come here to adjust the model settings. Depends on whatsoever you want your a result to present. So then, well, if you are interested in main effects, post factorial, and so on, so that's not relevant yet. And I don't want to bore us with all the. So one thing about analysis is that the more you do it, the more you know. So it's when you come across certain data, you get to learn about more models that works for them, that works better for them. So, sorry, I'll just go ahead and then click continue to generate results. So look at it. Now, because our outcome variable here has more than two groups. The outcome variable here is religion. Look at it. So is the way it's going to report for, unlike binary logistic regression that is reporting only the you can see only the covariate, but for multinomial is going to report for each groups using one as reference. So this Muslim here, the value here is okay. So this is the beta. Then again, we come to exponential beta. So this value here is the value for the odds ratio of ethnicity predicting Muslim. Are you getting it? So this simply is saying that John is ethnicity Nigeria. Okay. Okay, wait, let me wait. Sorry. Excuse me, let me check. Hello? Okay. Sorry. Okay, we've selected the appropriate. I expect the I expect the results to show each. So I guess this is one of the issues with the SPSS output again. So the reference here, remember we did not select first as reference, and SPSS uses the last group as a as the reference category. So is the group order is used as reference category. See what is happening here is so the result here is for the first group in ethnicity. Let's go and check the table. Okay. So we may need to even run like a summary, like a frequency table to recall the Muslim ethnicity, each other one here, then age group. Yeah, so I'll click that. So this is just to help us understand the groups. Oh, no wonder we have a lot of groups here. So your data makes sense if you clean them. But this is not the last day. I thought we cleaned this data up the other time. I guess I'm using the wrong time. Guess I'm using the wrong one. Okay, sorry, please. Okay. So well, sorry, this is not the cleaned this is not the clean variable. That's why the result is not looking that nice. So well, simply put, the first group here, this ethnic group here, is the okay. Look at it. This is the first group, equal. So that's the equal group. So that's the one the result is presented here. And then for Catholic, so what it does is it's going to pick each group of the variable. It's going to replace them against each categories in the it's going to report them against each category in the outcome variable. That is, we have Muslim, Catholic. So it's going to tell us predictors of Muslim, uh, tell us Catholic, tell us other Christians, and then tell us traditional. So that's what it's the way multinomial logistic regression works. So I think what we will do is for our project, we are going to get to do. Please, I like us to try as much as possible to do inferential statistics in our project work. So please let us try and then work on that. I don't know if anyone has been able to access the demographic and health survey data for use. So please, we need that. So I'm going to stop here. I'd like to ask if you have any question. So please, if you do, kindly go ahead and ask your question now. Okay, please, if you have any question, please go ahead and ask. Lekan, Lekan, do you have any question? Adetayo, do you have any question?
Oh, no question for now. See, after you have
No.
done this page, over the
Okay. Okay. So, Precious, I don't think you joined the last class, right? Precious Onifa David, were you able to join the last class? Okay. Anyways, if there is no question, we're going to call it a day. And I want to wish you the best, a blessed week ahead, and the best in your endeavor in your use of SPSS. Like I said, we already have a WhatsApp group, so please go ahead to practice this. When you encounter any issues, if you cannot ask us directly, put it on the group. In fact, I think you should put it on the group first because all of us will see it there and you have the benefit of getting answers from a lot of people, which increase your chances of being responded to early enough. So just put the question on the group. If you have any issue, put it there, we'll respond to you. So thank you, everyone. Do enjoy the rest of, the new week. And yeah, thanks.